In this video lecture, I will discuss some basic fundamental of the Quink's method, which we use to measure the magnetic susceptibility of FeCl3 solution. So, in general, we use this formula, that is chi is equal to 2gh upon capital H square, where small g is acceleration due to gravity and this small h is the height of the level, and capital H is the intensity of the external magnetic field. So if suppose one have to calculate the susceptibility, mass susceptibility, so then that time one use this particular formula 2gh upon capital H square, where the slope between small h and h square from graph is used to find out the value of chi. But as you know that in this particular experiment where we measure the magnetic susceptibility of FeCl3 solution by Quink's method, what basically is the region behind of the level, sometimes it raise up and sometimes it fall down from a position that is equilibrium position. So what is the reason behind of this? You have seen this experiment in this way. This is the block diagram of the experiment. These are coils. This is basically electromagnet in which you insert the Quink's tube. This is Quink's tube. Sometimes it is known as U tube. So these N and S both are magnetic pole and known as electromagnet, right? So we keep this Quink's tube or U tube inside these two magnet, the two poles basically. So the main purpose of this lecture is to drive a relationship for the magnetic susceptibility. So to understand that idea, we need some basic concept. These are given by this way, that mu or relative permeability is defined by 1 plus chi, and B is equal to mu naught H. Here chi is equal to m upon h, that is the ratio of two intensity. Intensity 1 m, that is known as intensity of magnetization of the substance, and capital H is the intensity of the external magnetic field. So one can write that m is equal to chi into h. If I put the value of chi from here, so that is mu r minus 1 and h from this relation, so this m becomes mu r minus 1 b upon mu naught, and ultimately chi b upon mu naught. So this is equation number 1. So before I proceed further, I want to describe a little bit about the experiment, that block diagram. So as I have already mentioned it, but now the magnetic field is basically along the z direction. This is the z. So magnetic field component which survive here, that is Bz in our calculation, and x is the vertical direction in which basically the level rise up or fall down. So here this material is kept in the tube. So in the presence of external magnetic field, the level basically rise up from the equilibrium position when this material was present in the absence of external magnetic field. And now because of the external magnetic field, what is happening? The level basically rising up, and as a result from this side, left hand side, it will fall down. So the amount at which how much basically it rise up from the equilibrium position will be same, right? So here h is basically it falls from this position and it basically rise up with the same height. So these are basic points in of this theory, where we will try to develop a formulation for the magnetic susceptibility, how basically magnetic susceptibility formula is derived, and what is the reason that the level rise up and fall down in the presence of external magnetic field. So these are two main motto of this lecture. Number one, that why and how the level of liquid rise up and fall down, and second, what is the formulation for the magnetic susceptibility in the Quink's type of experiment. So the first point starts now, that is force. So what is the nature of the force, and how one can define that force, in which term? This starts from this statement that force on a magnetic dipole of moment. Here magnetic dipole exists in the liquid, in this liquid of FeCl3 solution. There are magnetic dipole, and the moment of those magnetic dipole is defined by M. So when we apply the external magnetic field, a force basically exerts on the magnetic dipole. You remember that you can understand it by this way, that I have a magnetic dipole north and south in the presence of external magnetic field. So what will happen in the presence of external magnetic field? If this is N and this is south, so N will repel to N and S will attract towards this side. So a torque basically exerted on it, and because of that this magnetic dipole starts to rotate. Or on the other hand, you can say that external magnetic field try to align this magnetic dipole into the direction of the field. So this is the direction of the field. So by this way, similarly, we have to derive the result. Here magnetic moment, magnetic dipole of moment M due to an applied magnetic field B is Fxm. Fxm, why I am writing Fxm? X means that this force will apply either on upward direction or downward direction, like here, in the presence of external magnetic field. Right now I am focused on this particular area, so it will basically rise up. So that is the positive X direction. So X relate to that by this way. M is the moment of this magnetic dipole. So force on that magnetic dipole will be equal to Fx mx dbx upon dx, my into dby upon dy plus mz dbz upon dz. These are force component along the x direction, y direction and z direction. The main idea of this force, or the detail of such kind of force, is basically you can find out it from Boyer paper in American Journal of Physics that published in August 1988 in this volume 56. Right, the title of the paper is The Force on a Magnetic Dipole. So if you want to know more about this force, then you have to follow this particular paper. So from there one can find out the force on a magnetic dipole. Right, so that force is defined by the magnetic moment and the gradient of the field. So now one more important thing, that M we generally define by this way: strength of a pole into distance between the two poles. So P is equal to 2 ml. The force per unit volume experienced at a point in the liquid in the U tube is given by, will be equal to, you have seen this picture, the force is applying on upward direction, that is the x direction, and magnetic field is along this direction, so that is along the z direction, so Bz. So the total force per unit volume, so force per unit volume experienced at a point in the liquid in the U tube is given by Fx, U volume, unit volume per unit volume is equal to chi beta z upon mu naught. This is m. As you know that I have already defined capital M, that is the intensity of magnetization, is equal to chi b upon mu naught. But before I show you this particular result, I want to tell that this intensity of magnetization is an important quantity and have enough detail. Without of this intensity of magnetization understanding, one cannot explain the classification of magnetic materials, or basically what happens inside to the materials. So information of the magnetic intensity of magnetization is very important. So I will discuss in the second part of this lecture totally about M, but right now the target is about to understand the nature of the force which exerted on the liquid, and because of that the level rise up and fall down. So the force per unit volume is equal to chi Bz upon mu naught, and this factor is m, and the second part, gradient of the magnetic field, is this one. Here I am writing dBz upon dx. B I have considered along the z direction, and variation of this magnetic field along the x direction, that is gradient of the magnetic field. So force per unit volume is defined by this way. Now the second part of this comes when we introduce this magnetic field in horizontal direction throughout the volume occupied by the liquid. So now the total force, basically when we are applying, or we have applied already, the magnetic field along the z direction, the magnetic field force on magnetic dipole per unit volume will be equal to chi upon 2 mu naught into d upon dx bz square. So we have just modified the law, or you can say rearranging the terms. In earlier slide you have seen that force on magnetic dipole per unit volume is equal to chi bz upon mu naught into dbz upon dx. So instead of writing bz here and there, we are just modified the formula by this way: chi 2 mu naught d upon dx and bz square. You can see it again here. So the formula is chi bz upon mu naught into dbz upon dx. So instead of writing this, we are writing right now chi, this chi upon mu naught, this we just multiplied this factor by 2, because when we will differentiate this bz square, so 2 will come and that 2 automatically cancel out from it. So this is the new way of writing this particular formula. So here we have the idea of force on magnetic dipole. So that is in terms of the magnetic field and in the susceptibility. So we know that force is the negative of the gradient of the energy, right? What is it means? We can define force in this way also: F is equal to minus du upon dr, where u is the energy. So negative of the gradient of the energy. So we know force is the negative of the gradient of the energy, which is proportional to b square. So if I define this energy u, that will be equal to 1 by 2 b into h, and again H is equal to B upon mu naught. So here when you will put the value of H, that will be B square upon mu naught. So this force is directly proportional to the B square through the term 1 by 2 B dot H per unit volume. So in this particular case, where we are trying to find out the force on magnetic dipole in per unit volume, that is basically this one. And right now from this statement we are saying that one can derive this result or the force from the energy also, where force is defined as the negative of the gradient of the particular energy, right? So the force acting on the element of area A. So now we consider an element of area A and length dx. So suppose this is the case. Here I am just trying to find out the force. So length will consider like this one, so dx is the length, and area will consider like this one, like this circle is drawn. So area of that circle is A, and this one height basically, or segment, this segment or element is of length dx. So the force acting on the element of area A and length dx of the column of liquid is Fx A dx. So the total force F on the liquid, so this is the force on a small element of dx, and now we are trying to find out the force, total force on the liquid. So for that what we have to do, we have to just integrate the force within the limit of x. So here F is equal to A, F that force, and the integration of it with respect to x. So how we define earlier the force on any element, Fx A dx, right? So now put the value of Fx, and that Fx is equal to what? That Fx is in terms of, first we derive in this way, chi beta z mu naught dBz upon dx, and then after we modified it in this way, F is chi 2 mu naught into d upon dx bz square. Now I have to put this value to find the total force. So A chi 2 mu naught integration with respect to x dBz square upon dx. When we solve this integration, we found A chi upon 2 mu naught b square minus b naught square. So this is the total force, where the integral is taken over the whole liquid, right? So earlier we have considered the force on a small element and element of the liquid, and now we have considered that force on the over the whole liquid. So this means that B is equal to the field at the surface between the poles of the magnet. So what is this B and what is this B naught? B is the value of magnetic force where between these two poles, and B naught is somewhere at any other places. So B is equal to the field at the surface between the poles of the magnet, and B naught is the field at the other surface away from the magnet. So this is the total force which is applying or exerted on the total liquid, and because of this total force the level either rise up or fall down, right, in the Quincke's tube. So now when this rise up or fall down, the level of this liquid will stop. What is the condition for that? It's have a condition, and it's looks like as the upthrust force, similar to that. So now suppose the level of liquid is rising up, so at what time it will basically stop? What is the condition for that? The liquid moves under the action of the total force F, right? Total force F we have defined here, and because of it rises up until it is balanced by the pressure, right? So this force is balanced by the pressure exerted over the area A due to height difference 2h between the liquid surfaces in the two arms of the U tube. So this is a tube, this one is the tube, and as we have shown in earlier case that height of this, you can see this situation when this line correspond when there is no external magnetic field. So level towards this side, this arm, and level to this arm was same. But when you apply the external magnetic field, so because of that its level rises up, and the force behind of it we have already discussed about it, and because of that it rises up, but it moves, and at what time basically it will stop? It will stop when the pressure exerted over the area A due to height difference 2h. Height difference we are taking here 2h, coming from h this side below the level and above the level. So this is the total difference between the liquid surfaces in the two arms of the U tube. So this force which exerted on the magnetic dipole is balanced by the pressure between the two arms. So now allowing for the susceptibility chi A and density rho A of the air. So now we have introduced two more parameters. One is the susceptibility and second is the density of the air which the liquid displaces. It follows, so the liquid basically displaces it from the Quincke's tube. So the relation now becomes A chi minus chi A, B square minus B naught square upon 2 mu naught, that is equal to 2AH rho minus rho A into G. So here if you see this AH is equal to the volume. So this formula is rho Vg, where V is the volume, right? Rho is the density and G is the acceleration due to gravity. So it's similar to the upthrust formula. So now the form of this formula is chi minus chi A, B square minus B naught square is equal to A cancel out. So the rest of the term chi minus A, B square minus B naught square is equal to 4 mu naught H rho minus rho A into G. And if I write it properly in terms of chi and chi A, the formula looks like that. Further, there is no contribution of the air susceptibility and the density of the air, and similarly B naught is equal to 0. There is no role of magnetic field, this B naught. So after this one can write the formula for susceptibility. Chi is equal to 4 mu naught H rho G upon B square. So one can derive the susceptibility by using this formula, where chi is equal to 4 mu naught H rho G upon B square. So further, if we see this formula carefully, here I have defined that derived this chi is equal to 4 mu naught H rho G upon capital B square. We know that B is equal to mu naught H. So when I will put this value of B here, so it will be 4 mu naught square h square, mu naught cancel out, so one term is there, so that will be 4h rho g upon mu naught h square. So this is chi, so this is susceptibility, and if I have to find out the mass susceptibility, then I have to divide it by rho, and then that time it chi mass susceptibility will be equal to 4h g upon capital H square and this mu naught. Right, so now this is the formula for mass susceptibility. So if I have to find out the value of susceptibility, I have to find out a result, or is result from the graph by plotting between h square and small h, where h is the intensity of the magnetic field and this small h is the distance basically by which a solution, by which a liquid rise up. So for different value of the current, and as a result of different value of the magnetic field intensity. So this is almost a straight line. I will show it by taking the proper reading from this experiment in the next video. So I have to take a slope from here, right? So this A B C, so A B upon B C, slope will be AB, that is H, and this BC is equal to in terms of H square. So this H upon H square I have to find out from the graph, and then after I have to put that value here. G, this H, this is G, acceleration due to gravity. So by putting this value of this and constant mu naught, so one can find out the mass susceptibility, or in general the susceptibility, magnetic susceptibility. So what is the important point here? As I have told you earlier in the first slide, that we define here the magnetic susceptibility in terms of the ratio of these two, that is m upon h. M is the intensity of magnetization of the substance, that how much that substance is magnetized, and h is the that field by which this substance is basically going to magnetize or has been magnetized. So there are two fields. One field is associated with the material or substance, and the second field by which you are magnetizing that substance. So this chi is the ratio of those two intensity of the magnetic fields. So this H can be understood very easily. This H is the magnetic field intensity, and this M we generally say, and I found that we generally use this word intensity of magnetization before going into the depth of this particular idea. So in the next part of this video I will discuss, and totally will remain focused on the intensity of magnetization, that how one can define the intensity of magnetization, because without the information of intensity of magnetization no one can understand the categorization into the magnetic materials. As you know that magnetic materials are characterized into the diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, like this one. So to understand that idea, basically it is very compulsory and important that one should have clear the idea of intensity of magnetization, which we have written here, and that is associated only with the material, what basically is happening inside the material, right? So chi is defined by the ratio of these two intensity of one is intensity of magnetization of the substance, and second is the intensity of the external magnetic field. So in this lecture I have just tried to show that what is the reason that level of liquid rise up in the presence of external magnetic field, and the type of force and that formulation. So thanks for this.